So let's look at this bifurcation diagram thing. And why won't it let me? All right, we'll do control click and see if that works. Uh-oh. All right, we can't do it. All right, so because the internet's down. All right, so let me try to draw it. Let me try to explain what this bifurcation diagram is.
My internet's working. It's just there's something.
Okay, well, so here we have A.
Kind of looks like that one graph I had late last night.
And we're going to look at, we're looking at f of x equals a x 1 minus x. Okay, then on this axis we're going from 0 to 1. Okay, now let's take a particular value of a. I'll call this a prime. Now, you know that when you run this map, right, you run this map and you have this here, it's going to bounce around for a while and then maybe it'll settle down. Okay? So you don't want to keep the initial bouncing around. You just want to record where it settles down to. Okay? So you're going to let it, I'm going to start it at the middle. And I'm going to let it bounce around for a while until it settles down. And then I'll plot the points where it settled down. Now, you saw that it's not necessarily going to settle down at one point. It might be period 2. It might bounce between 2. It might bounce between 3. It might bounce between more. Okay. So what I'm going to do is I'm going to, so I want to find the points where f, and here I'm going to say x comma a, settles down to. Where, when I say f of x comma a, f of x comma a is equal to a x times 1 minus x. Okay, so suppose this one is f of x a prime, and suppose that when I use a prime, it settles down to this one point. So I want to plot this one point on this graph, on the y-axis. Suppose it settles down to, let's say it settles down to 0.75. So I would want to plot 0.75 on that graph. And I'm going to do this for lots and lots of values of a. And as we saw, as a increases, it gets more unstable. So what happens is that there's a value of a where it splits. And what the split means is that there's no longer a fixed point. There's a period 2 point. It's bouncing between 2. And then what happens is it splits again. And you get a period 4 point. And what that means is as the point bounces around, it's bouncing between 4 points in the orbit. We saw this in the Mandelbrot set. If you remember when we did the cardioid, I think you were there. Mm-hmm. We did the cardioid. The points in the cardioid all went to a single point. The point in the circle to the left of the cardioid, those points bounced between 2. And then we did a little exercise, and another one we had them bounce between 3. So what you're going to see is that in this case, as a increases, you get these cascading divisions like this. Then it goes to period 8, then it goes to period 16, and it goes bigger and bigger and bigger. So what happens? Eventually, it reaches complete chaos. Well, that means that if you had a realistic system, that means that it's all over the map. It's not going to settle down anywhere. I mean, you do have chaotic phenomenon in nature where things don't settle down. It just seems like totally random.
Does as we move out, this, I know, and maybe this is just the way you're drawing it, does that split become quicker and quicker, and that's
Yes.
how we move to chaos where it
Yes,
is?
yes. This is a convergent series. These distances form a convergent series.
Oh, okay. So yeah.
So it reaches
converge.
at finite time. It
Wow.
reaches infinite. It reaches infinite divisions.
Okay.
And then you get some weird stuff over here. Now, if you notice here, this is period 2, this is period 4, this is period 8. You're doubling each time. What about the odd periods?
About the what?
What about the odd periods? There aren't any odd periods here. The odd periods come later after the chaos happens. So there's a famous theorem called period 3 implies chaos. And I think I'll have to look, but I think that what happens is the odd periods go backwards. You have big odd periods, and then they get smaller and smaller, and then 3 is the last one. So you'll see that in the diagram. And so what I wanted to do today in class was to actually construct this diagram.
Let's do it.
So you have it on the paper.
Give me a pencil.
So I made this pseudocode outline, right? So let me just talk through it. And for those on the recording, this will be on Canvas. So you have initialize, right? So here you have instead of A, I used it says Rmin and Rmax. Sorry, that should be Amin and Amax. Sorry about that. So you can correct that. Then you have min iter and n iter. So what does min iter mean?
The minimum number of iterations?
Well, like I said, you want to iterate it until it settles down. So what you're going to do is you're going to iterate the function without recording the positions for min iter iterations, and then you'll start recording them up to n iter, and then you're going to plot those points. All right. So you can see that xvec and yvec, these vectors have length n iter minus min iter, because the first min iter iterations, you're not going to record those. So you don't put those in your vector. Then you record the other ones. That's n iter minus min iter. Okay, and then you can see that avec is na equally spaced values between amin and amax. So you're chopping the a-axis up into points, and then for each one of those points, you're gonna compute this set. And when you plot the points on the set, you're just plotting individual points. You're not going to plot a line. So you'll want to plot a dot marker when you do the plot. All right. So I think you can follow this code and see if we can finish this off tonight. Give it a shot. So I'm going to stop recording.